So, hi everyone. So today we have a great guest that I'm very delighted to introduce. If you do not know him, but I'm sure everybody know him. So Jiatao Gun is a research scientist at Facebook AI Research. His research interests lie in applying deep learning approaches to natural language processing problems, specifically building an efficient, effective, and reliable neural-machine translation system for human languages. So far, he has published several papers in top-tier conferences such as ACL, EMNOP, NeurIPS, and unclear. So Jato is going to be talking about his recent the work, which is very exciting. Welcome, Jato.
Okay, hi, nice to meet you. It's very great to come back here. So I have an internship 2 years ago. I'm working with Hania, and it's a very nice time and journey. So yes, I was starting from introduce myself. So Akiko already said. So I'm a research scientist at Facebook AI Research in New York City, and I have my PhD in University of Hong Kong, and then before that I have my bachelor in Tsinghua University. So before talking to our topics, I'll first take some time to discuss what my research interest in at FAIR. So my research mainly lies into three aspects. So one is the low resource and multilingual neural machine translation, and where we published papers about analyzing why zero-shot neural machine translation works or didn't work. We also have one paper accepted by AAAI next year. Is discovering the byte-level subwords, which would be a better way to modeling multilingual things. We also have some ongoing projects working on to combining pre-training on multilingual setting, and which will be useful for low-resource MT. The second aspect of my work is evolving the advanced methods for natural language generations. So I was very interested in building a new way to generate not a generate sentence from left to right, but generate in a very different ways. For example, we have a paper at TACO, which is to develop an insertion-based generation to generate words by using insertion process. And we also have a UX poster, which will be next week. If you will come here, it's great to chat with me in detail. So it will not be discussed in this talk. It's using the insertion and deletion words to generate a sequence in an iterative way. A third part for my research is involved in the multimodal, which is especially in speech and text. So we're working on end-to-end speech translation with my colleague in Menlo Park. We submit a paper to IWSLT. And especially we were organizing another simultaneous speech translation share task in next year at IWSLT. So if you are interested, you're welcome to participate. So I take some time to discuss my general interest. So today's topic is a bit small but concrete finding in our recent work. So we were discussing about the sequence level knowledge distillation, which is not a new thing. First, the knowledge distillation is originally proposed by training a weaker student classifier on the targets produced by a stronger teacher model. So it's generally in a classification area. So if you have a target, it's not using the ground truth labels to train a classifier. You're using the teacher's models, the logics, to produce some soft labels, which soft label will train the student in a maximum cross entropy. In the context of sequence generation, so the sequence level knowledge distillation, instead using the hard targets instead of soft to train the sentence. So what you can be seeing is given the model, we first do some decoding method to find the best solution translation or sequence, and then using that sequence to supervise my current model. So the sequence level knowledge distillation can also be seen as a soft version when this temperature goes to 0, then the soft label will become hard label. So it's actually the same thing. But the good thing is because we cannot really maximize the target sequence when we're doing the decoding. So you're always using some kind of approximation, for example, beam search to find the best solution in this case. So let's discuss in detail about sequence level knowledge distillation. So I put a figure like this, and this figure will be using it again and again in the talk. So it's generally in 3 steps. The first step is to train a teacher model with the golden labels. And the teacher model is like this. And the label is coming from some data D. And then once the model is trained, we're using this model to generate the data. So we're using any kind of decoding method to get some data Y star. And then when we have the X and the Y star, we're using this kind of pairs to train a student model, using the same way as when we train teacher model, like a maximum likelihood. And here I'm using dashed line to show that these are the same thing. So teacher model are bounded, and the target, when we have the target set, we use it to supervise the student model. And this method actually works extremely well, especially when we use it for model compression and for any other tasks. But there are several questions if you look at this. So at least to me, first is, so this method didn't tell you how to choose the student and teacher model. Usually we think about we need to have a stronger teacher and then we have a weak student. But what if they are the same, or what if the student is even stronger? What will happen? A second thing is, if you look at the decoding time, we didn't actually have some correspondence between these two X. So the sentence may come in from the same data set or may come in different data sets. So what if we have more data to do the distillation? And the third thing is why and how this distillation works in generation. So as we all know, sequence generation is quite different from the classification. So it's still unclear why this kind of noise distillation will improve the model, because after all, we are using the fake data to train the model. We are not using the real data. To answer these 3 questions, we are actually tackling this into 2 aspects, actually. So one is how to choose the model, and second aspect is how to deal with the data. So the first work I will introduce is called Understand Noise Distillation in Non-Autoregressive Machine Translation, which is a joint work with Trentin and Graham. And this paper was submitted to unclear 2020. So before that, we need to discuss what is non-autoregressive machine translation. So we all know that standard machine translation models are autoregressive, which means that we decode the target sentence step by step. So each word will take condition on the previous generated word and predict next word. And this is good because it's very strong, and it can in theory model arbitrary distribution of the sequence. However, it is slow because you need to always wait for all the previous word to predict the next words. And implementation-wise, it can be very slow, especially when we want to do very complicated model like a 12-layer transformer, like a GPT-2, something like this. So instead, non-autoregressive translation trying to predict the sequence in parallel, which we model it like independently predict all the words at the same time. And of course, it's fast because we can take the advantage of parallelism. We can predict all the words at the same time and compute everything, especially on GPU. But of course, it is weak. And all the words are actually are dependent with each other. We cannot really assume they are independent and we predict them. Usually, the non-autoregressive models are much worse than the autoregressive models. So in practice, no one really using the pure non-autoregressive models. There must be some intermediate representation Z, which trying to capture the ignored dependency in the output space. So for example, we can write everything like this. We model some immediate representation Z, first predicted by X, and the conditional Z, we predict all the words at the same time. And based on different Z, there's typically 2 types of non-autoregressive models are considered. One is if Z is a kind of standard latent variables, which may be continuous or discrete. And we call it VAE-based NAT models. A second thing is the can be immediate partial generation. For example, we first generate something and then we refine it on that. As long as we didn't stop decoding, everything in the middle are the latent variables. So we all call this like a refinement-based models. So I listed some papers here, but I didn't have time to spell out. So then let's talk about non-distillation for non-autoregressive models. So as we all know, based on our discussions, we all know that non-autoregressive models are weaker than the autoregressive model, right? So it's a nice standard way to do the non-distillation because typically we want to using a stronger model to distillate the weak model. And also in our discussion, we assume that all the data are the same. So both the student and teacher model are training on the same source sentence. The only difference is that the teacher model training is using the real targets, Y, and the student is training targets produced by the teacher models. So here's an example of performance with or without distillation for non-autoregressive models. So every performance is tested on WMT English-German dataset. And the models are distilled from the same autoregressive transformer model with Bruce score like around 27. And then we tested on 3 different models. The first one is a very simple non-autoregressive model. There's no any latent variables. So you can see it gets like 11 Bruce score, sorry. And second thing is the flow-based network model, which using a latent flow as a latent variable, which can get a better performance compared to the naive one. So it means that latent variable actually captures some of the dependencies. And the third thing is we recently the newest paper, which using the insertion and deletion methods to do iteratively refine the translation. It actually can get a very good performance, like 25, but still it has at least like 2 Bruce score gap between the autoregressive models. But just with discretion, all the models just improve a lot. Even for the very strong model, it can also improve around like 2 Bruce score. And for the very naive model, it can improve like 8 Bruce score. So this means that the knowledge distillation is really the key for making these kind of non-autoregressive models work. So why it happens? The original paper from the non-autoregressive model paper argues that the kind of non-autoregressive models will suffer the problem called multimodality. And there's an example which I use again and again, but it will be very easy to see. So, for example, one source is I want to translate thank you into German. There are several ways to translate into German, like vielen Dank, Dankeschön, and Dank, and everything are correct. But if you model them in a parallel way, so if we predict them in parallel, we cannot avoid to produce something like a Dank or vielen schön. They're actually wrong, but for non-autoregressive models, cannot make them different. However, for autoregressive model, we can first predict the vielen and then condition on that to predict Dank. And first predict Dank, condition on that to predict schön. So this is not a problem for general autoregressive model, but it's a problem for non-autoregressive models. Then our assumption at the time is that distillation helps to reduce this kind of multimodality. So in this paper, we want to carefully analyze this, how this multimodality is reduced. So when things are unclear and too difficult to explain in sequence generation tasks, especially like machine translation, I think it's a good idea to look at some toy cases. For example, the other toy example is we create a synthetic data set combined with 3 language pairs, as English, German, English, French, English, Spanish, all from the Europal data set. And we make sure that every English sentence corresponds to 3 different languages. Like every English sentence will be translated into 3 different languages in the data set, and we don't provide the language ID to them. So in this case, we are manually creating some multimodality in the data. So every sentence needs to be translated into 3 times in the data. And we force the model to memorize that to train either autoregressive model or non-autoregressive model directly. And during inference time, we also don't know what language will output. So we just give the English sentence, and the model will choose whatever it learns to do the translation. So what will happen in this case?
will be aligned, like the English source is the same?
So yeah, so for example, we have like 1,000 English sentence, then we have 1,000 German. So we have 3,000 examples, like 1,000 English, 1,000 German, 1,000 English, 1,000 French, 1,000 English, 1,000 Spanish.
But the English is different, right?
They are the same English.
Same English.
Yeah. So we're just trying to make sure there must be some multimodality in the data. And then what will happen? So clearly,
you said that you have autoregressive and non-autoregressive models. Isn't the difference just in the decoding, or you have actually different models?
it's different models.
Okay.
So because the way you decode, I mean, the autoregressive model decode the word like left to right, right? Mm-hmm. And non-autoregressive model just predict everything at the same time. And it also affects the training, like because if you train in maximum likelihood, the logics will compute differently, right? Okay, so there's 4 figures to show that. If you look at the first 2 figures, the first figure is so we want to visualize how the model captures this kind of multimodality. So we want to visualize the mode of language ID. We approximate the language ID by averaging this. This equation looks quite complicated, but to be simple, it's like this. So I take a model, I input an English sentence, I output some sentence. And the some sentence, I can calculate each word, which this word is coming from English, coming from French or German or Spanish. And I average this probability, which can be an average probability of this sentence belongs to any languages. It's a very rough approximation, but it actually works quite well. So if you're using this kind of approximation, you can see that autoregressive models can almost good to generate some sentence. Like it will either generate German or French or Spanish. It won't generate something in the mix. So it means that if the model will automatically during decoding time to choose the mode, what language you want to generate. However, for non-autoregressive models, everything's mixed. So you cannot completely classify what language I want to generate. I want to generate German or generate French or generate Spanish. Everything is in a mess. So that means that this kind of model is really, the problem is the multimodalities, right? Then what we do is we're using the autoregressive model, the targets, to train a new models. So we're using that targets to train a new model on an autoregressive model, and then we visualize the modes again. So in this case, because the autoregressive model, when you decode it, we automatically choose the mode for each source sentence. And when you choose the mode for each sentence, we train the non-autoregressive model again. Then the autoregressive model will never, or at least not so serious to output something like mix. It will also generate something like either German or French or Spanish. And the other comparison is this figure. This figure shows that I will randomly, given the 1,000 sentence, as Hani just asked, if we have 3 targets, we can randomly select one language as its target. So it's also kind of reducing the modes, which is based on random. If you randomly reduce the modes, it works worse compared to if you have an autoregressive model select mode for you. So it means that the distillation is actively selecting the modes for the data and then training on the autoregressive model can training on that. So in spite from the visualization on the toy data, so we can propose something using the data uncertainty to measure the multimodalities, or we call it complexity in a general purpose. So how to do this? So we're using a token level conditional entropy to measure the data's complexity, which will be very simple. So this equation means that we first generate the data. So data may generate from the autoregressive model or non-autoregressive model. And then we apply an IBM, or we apply the fast align, the alignment model on that. We can find and when we have the alignment model, we can get a line table. Using the alignment table, we can compute the token level entropy for this data set. So this is also an approximation because it's not a real complexity of the data, but we using a proxy, which is an alignment model to get the entropy of the data. So how this works? So if you're using this measurement to measure the data set, you can see that when we're using the every sentence with corresponding to 3 different languages, the complexity is like around 3.6. That is the average token level condition entropy, which is quite high. However, if you compare to the data coming from the autoregressive models generation, the complexity just drops to like a 2.6. So, and the results also show something like this. So it means that the first is autoregressive model really is the distillation is trying to reduce the complexity of the data. And second thing is our measurement also shows this kind of correspondence. And later we can always using this measurement to assess the real data sets, not in this kind of toy data sets. And to be compared with the random selection model can get like 3.3, which is in the middle of between these two. So it's get better than the completely everything's masked, but also it's worse than using an autoregressive model to select. So we also propose another measure called faithfulness, because when we're doing distillation, if the model produces something is far from training data, this kind of measurement cannot capture this. So in our case, we're using the same alignment model, but compute the KL divergence between the real alignment probability and the distilled probability, and using that KL divergence to measure the faithfulness of this data set. So now we have all these 2 tools. So we perform an extensive study on a variety of non-autoregressive and autoregressive models with this kind of complexity and the faithfulness. So we picked the one data set. It's still the English-German W14, but we using 4 different autoregressive teacher model and many non-autoregressive student models. So here we show the baseline scores. So we can see when we're using different teacher model from tiny, small, base, big, the blue score just get improved, and because the parameter is getting more and more. And for the non-autoregressive models, we also rank it from the weak to strong. So it's really difficult to measure the capacity of a model in a very detailed way, because different model may using different ways to inference. So for example, the non-autoregressive model, sometimes their parameters are the same, but if you do iterative refinement, it just gets better performance. So right now here, I'm just using the blue score get on the real data to measure the capacity of the model. So if the model gets better performance on the real data, it means the model is much higher capacity. If the blue score is worse, you just get a lower capacity.
What the pass iterations like?
So this is only the pass is only useful for the pass and iteration is only useful for the non-autoregressive models. So here, one pass means that how many time it takes to do the one forward process. Forward computation. So usually, when I put here something like why the flow seek is 13, it's because this model is using a flow to compute the latent variable, which is quite deep, and this model, although this model is a non-autoregressive model, but it takes a long time to compute the prior, which actually costs a lot of time. So this is approximate the time to do one pass. And the iteration means for model which is based on iterative refinement, it may need multiple iterations to get the translations. And for example, like this is an insertion transformer proposed by Google, which is a log to n time. So you first predict one word, then predict the 2 words, predict something like this. And for other models, maybe using a fixed number of iterations. So I just list all the configuration here. But right now we just need to care about the blue score part. So the blue score shows, roughly shows the capacity of the model for these scenarios. So then let's first analyze the distilled data. So as we mentioned, we have 4 teacher models, right? So it's tiny, small, base, big. So we first visualize the proposed complexity and the KL divergence. The complexity is the conditional entropy, which shows that this is a blue curve, and it's quite monotonic actually. If you increasing the data set, the model's output, the complexity is getting bigger and bigger, but the real data is much, much more difficult compared to all the data set coming from the autoregressive model. So which means that at least the model's output is still much easier to run compared to the real data. On the other hand, because the model gets more complex, then the faithfulness, the KL divergence is getting smaller. It also means that because we have a stronger AT model, then I will produce some data set which close to the real data. And it should be nice because what we really want to learn is to learn from the real data. We also plot the training set blue score, which you can see that the blue score is very correlated to this, our proposed KL divergence faithfulness. So it also shows another thing about the data set. The another thing I think is interesting is we also analyze the reordering score for this translation. So we pick one score called the fuzzy reordering score, which will measure the decoded sentence, how it is monotonically aligned to the source sentence. So as we all know, that English, German are in different orders, right? So German words, when we on the back, they shouldn't be the same orders. However, if you look at this figure, you can see that. By the way, so the smaller the score is, it means that there's a more reordering it has. So the real data has the most reorderings, but for all the other autoregressive models, the reordering scores just monotonically drops when the model gets improved. And which also makes sense, because if the model is just weak, it will first trying to capture the easiest thing to run, because reordering is more difficult to run for the autoregressive models compared to the monotonically generated words. We also pick a data sample here. For example, this is the source sentence. I'm using the different colors to show different chunks of the words. You can see the real data set, the words actually reordering a lot. So different, for example, the 30 years are put here, and I don't know how to say, but it's different parts. They are completely crossed, and grammatically they're correct. However, if you're using distilled data set, it almost looks like monotonically, which may also explain why this kind of data set is more easier for the non-autoregressive model to run. Then we discuss what's the distillation strategy affects the process. So in default, we always using beam search to output the sentence here, right? But sometimes we may want to see, is there really need beam search? The answer is yes. We must use some beam search or at least some grid decoding method. Because if we're doing sampling, we will just increasing the complexity of the data. Again, it will get a much worse performance if you're doing sampling during this time. So there's no distillation at all if you do sampling. You must use some deterministic, you're trying to find the best approximation, which is beam search. You can get a better performance. Now we analyze all the non-autoregressive models we propose here and all the autoregressive teachers. So we put everything in this figure. So you can see, first, we always put the red curve here. The red curve means the teacher's performance. So even if the tiny teacher can get like 24 blue score, which is okay compared to these kind of non-autoregressive models. However, if you can see that the stronger non-autoregressive model is, this kind of non-autoregressive, the curve will getting closer and closer to these autoregressive models. And eventually, this model will get very close to the autoregressive model. And we also see that, the teacher model does not have to be the upper bound of the student, which we'll also discuss this question later. For example, for this Levinson transformer here, if we're using a small transformer to display the data and the training on that, we can get a better performance compared to the original teacher model. So
both are the same architecture? Both are small, right?
No, they're different. They're different.
The teacher is smaller than the
teacher, the parameter actually is smaller than the student. the parameter is smaller. But people may usually think about maybe when we set a teacher there, right? Using the data from the teacher, we cannot go beyond the teacher. But it is not the case for the knowledge distillation. So as long as you're optimized properly, you can all still be better than a teacher if you just train like this. The third thing is you can see that when increasing the capacity of the teacher model, so all the curves share the same patterns. So the non-autoregressive model, when we increase the capacity of the teacher, it first the performance gets improved, and at some point it drops. And we believe that at some point is that the data is too difficult for this model to capture, because we already see that the more the capacity of the teacher is, the more complex the data it becomes. So, and for each student model, for each non-autoregressive model, it must have some limit. And when you're beyond this limit, you cannot learn anymore. And you can see that this limit is actually different from all the models. The weaker the student model is, the limits are also much left. For example, this kind of vanilla models, it performs best on the transformer small. However, if you look at like mask predict or Levinson transformer, the best performance actually achieved at using a big transformer. So it means that when we develop any student models, we always need to be careful that what teacher model we choose actually affects performance. If we want to get the best performance on the student model, then we need to properly tune the better teacher model to fit for that. But that is also a very tricky thing, because we cannot really analyze what the capacity is. So we propose several ways to improve this kind of distillation. So one thing is to improve over the weak student models. Here we take the vanilla non-autoregressive model as an example.
Sorry, in the previous slides, do you have an autoregressive student anywhere or no?
No. So here, this paper for this paper, we're only using the non-autoregressive model as a student. But it has the same patterns.
So do you also see in the autoregressive student that as that it drops off if the teacher gets too big?
Yeah. Yes.
So we are doing a lot of teacher-student training. Our students always follow the quality of the teacher. If the teacher improves, the students improve with the teacher.
So I think there must be some. So if you fix the student, you keep improving the teacher's model again and again. I mean, there's some point is, I only try the thing I ask is I try the LSTM as a small teacher, and my small student, the teacher is the big transformer.
But these are not LSTM models.
They are also transform models, but they are non-autoregressive models. And there's maybe some possibility is like this. For example, this model is very close to the teacher model already, right? So if there's one model, the point is even on the right. And also, this is very depending on the data set. So for all these experiments I show here, I'm using the English-German data set, which actually is quite complicated. So if you look at the data set, it has many misaligned or a lot of wrong translations. So it's just increasing the complexity of the real data. So if we also do the same thing on another data set, for example, people usually using like Romanian English or similar language, which is much easier, the real data itself is not so complex.
How large is the training data? This is WMT 14?
Yes.
Have you tried going larger?
So we have some other experiments, but not in this paper, yes.
And how does it look like when you go larger in terms of training data?
You mean this is distillation or?
Yeah, does distillation improve for the non-autoregressive models when you have more training data?
So in this case, we didn't have comparison yet. So
okay. There's cases where the student is better than the teacher. I mean, we only saw it when there was additional data, right?
Did we ever see the student better than the teacher?
Where are we seeing this?
In his last bottom right, for some of the teachers,
I mean, just
for the small,
depending on the small, I mean, when you have a small teacher, right, so your student is stronger.
okay, so in that small case, the student actually has more parameters than the teacher?
Yes.
Okay, that would explain that. Okay.
We have not done that.
Yeah.
But this, I mean, this curve is just trying to say that, so even though the parameter is the same, so it may, a lot of things may happen.
Also, if
So-
you're not familiar with Yoshua Bengio's paper on thin nets, they intentionally try to do distillation and get higher accuracy out of the students than the teachers. It's not uncommon to see a small gain in accuracy on some students. But,
Yeah,
but Yoshua Bengio's work, they actually, that was their whole goal, was to get higher accuracy. So they developed additional tricks.
The other problem is that all this work is done on toy data sets. So the moment we do this for production, and we usually see it works very great, but there's always a small gap between teacher and student. But we scale this, so if this is a WMT14 data set, then our data sets are like 100 times larger than what is being used here.
And I agree with you. Whenever I've done massive data sets,
Yeah.
we've always seen that there was a gap.
Yeah, I think things will change a lot. We have a really large scale, and I think for large scale training, so the less you put the prior into it, usually you'll get a better performance. But here, I mean, the goal here, we're just trying to analyze when the student itself is like a low capacity, and the teacher, I mean, like non-autoregressive models. So how these things change, and we always see this kind of curve for all the models, at least for non-autoregressive models. I think it depends a lot of things like the model capacity and the data complexity itself. If the data itself is too easy, or I mean, I haven't tried the large scale thing. Maybe when the data set is large enough, then this point will also shift to the right. So yeah, continue for this. We have some improvements. So based on the distillation. So one thing is the ball and game network. So because we see that for the weaker students, we may need some easier data to train it, otherwise it will drop. So the good thing is we find that if we distillate your model itself again and again, so it's called ball and game, which means that you first train a teacher model, decode, and use the data set to train the teacher again, and then decode again and teach the teacher again. And you train it a lot of times, so you can see that the teacher performance will never drops. So, or at least it just as a point. As long as we're using the same data, the teacher model will never drops or never improve. However, the students will getting better.
Right? At least the first iteration of self-training should improve.
Yeah, we will discuss self-training in the second part. But here, because we're using the same data set, so we never include new data into it. So the performance will always stuck here. However, for the non-autoregressive models, the more iteration you have, it will generally getting better performance. And we also analyze the complexity of the data set. You can see the more reborn iteration it has, every time you get an easier data set, and when the data set gets easier, you get a better performance on the non-autoregressive models. So it's also an example how to, if we have a fix the weaker student, how can we get the better data set? We can just distillate the teacher model again multiple times. Another thing is if you have a strong student model, how can we further improve the performance? So there one choice is called the sequence level interpolation, which is also proposed by the original paper from from the sequence level distillation. And the thing is we're not only using the beam search, the best one, but also using the k-best beam search and then use Bruce score to select the best translation from this one. So it turns out that if you select carefully between this k, for example, I use like top 5 and then using this top 5 sentence and then using sentence brew to select the best translation, it will get a better performance compared to just using beam search, because we we naturally get a kind of stronger translation model, although it's not really a translation model, but because we just use it for providing the better data, then we can use it to train the stronger student models. But it's always a balance between, for example, if the data become too strong, then the performance will still drops. So we need to find the point where to get the student. So the code of most of the non-autoregressive models can be found in FAIRSIG. It's already implemented. So okay, so I think it's quite. I don't have too much time, but the second part we want to discuss is when we have what if we have more data. So we trying to revisit the self-training for newer sequence generation, and this is a joint work with Junxian He, Jiajun, and Macquarie. So why I put self-training here is because actually the basic data is the same thing. So the difference is previously we always assume the training data for train the teacher and train the student are always the same. However, what if we have more monolingual data? Because for the second part, when we decode the targets, we don't need the real targets here. So we can using the very much monolingual data to decode more data, the targets coming from teacher model. And to be simplicity, we assume right now the teacher model are equal size with the student model. So we don't using different model anymore, but we always using more data to train the student model. And there's also another difference is after we train the student model using the Y, you can always fine-tune the model on the real data again. So there will become a loop. So we're starting from teacher model, we training on parallel dataset, and then we generate targets on the monolingual dataset. And once we generate targets, we train a student model, and fine-tuning the parallel dataset again, and then decode again, and fine-tune again, and again. So it's kind of called iterative self-training. So how it works? So if you remember, previously I say that if you do iterative distillation yourself, you will never improve. However, if you adding more data during training, especially during training the student time, every iteration you actually get more improvements. So for example, we call the training on distillation data, it's called the pseudo training, and the training on the real data, we call it the training or fine-tune. So you can see that the first iteration, the teacher model gets like 15 blue score. And then we do the distillation and the training on the distilled data, we get 16.5. And when you fine-tune on that, the real data again, we get 17. And then for the next iteration, get improved and improved until something just converge. And there's one thing is not very natural is these two numbers. So for the first iteration, because our student model are the same sized. However, if we training on the student model, training the data that's the same from the teacher output, it gets better performance, which is actually not very natural because the model right now, there's no difference. They are all the same. However, we just becomes more, because we have more monolingual data, then we get a better performance. And this model is never trained on any real data set. It's just a trained data set produced by this 15 blue score models, but it gets better performance compared to 15. So we want to understand why this happened. So there are several hypotheses. The first thing we thought about is a decoding strategy. As we mentioned just now, we always need to do beam search instead of sampling. So we do it again. So if we do beam search and sampling to try different ways to get the target Y star and to train a student model, what will happen? It turns out that sampling do get worse performance. So it again shows that beam search will help you to find the better targets. So they are not actually the same size targets, the same size models. So beam search always find the better targets compared to your current model's output.
So the reason this is different from the previous graph where you showed it is because you are training the teacher on the student's output, not on its own output?
training the student on the teacher's output.
I'm trying to understand that the big green arrow.
Oh, the green arrow is a fine-tuning step. So once you get this model, we will fine-tune on the real data again. So,
So there's nothing going back from the student into the teacher.
there's nothing going back. So it just become a new teacher. So for example, there's teacher one, right? Teacher one train and teacher one decode, and then we have a student. The student is training on the teacher's output.
So what the box that's labeled student here is the teacher two.
Yeah, teacher two.
Okay.
It will fine tune on become a teacher two, and then decode again. So there's no loop go back to the original teacher. But right now, what we want to compare is these two numbers.
How do you get teacher 2? On which data do you get teacher 2?
So the teacher 2 will go back to the original parallel data set. So
all the data that you use for training the teacher 1, you do one once again on that data.
Yes. But before training on the, we first do self-training on the monolingual data, and then we fine-tuning on the same data training on teacher 1.
So you train the first teacher, you translate the extra monolingual data with that teacher.
Yes.
Then you train the second teacher with that monolingual data only, or with that as well as the parallel?
Yeah, so that's two numbers.
Yeah, so you first train with only the monolingual data.
Yes.
Then you fine-tune
on the parallel data.
On the original parallel data or the retranslated parallel data?
Original parallel data.
But fine-tune, not adding. You are not adding both to it. Just fine-tuning.
Just fine-tune. So
you never train on the two jointly.
We try. So we spent like 2 or 3 months doing jointly, and then someday I suddenly find that fine-tuning works better, and always works better. So I just.
What is the ratio between the data size here? What is the ratio?
Here for this figure is like the data set itself. We simulate a low resource case, so the parallel data is like 100K sentence pairs, and this one is like 3 million monolingual. So we also have a full data comparison later, so it shows the same thing. But here, what we want to compare is these two numbers. As you mentioned, this 16.5 is only training on the data coming from the teacher, and teacher 1. So the teacher 2 only training on the data from teacher 1, and it gets better performance compared to the teacher 1. And when we're doing sampling, its performance actually drops, but still get a better performance than the teacher 1. So there must be still something inside compared. It's not only the sampling makes it better. So then we find that, so actually we always turn on the dropout, which is common, right? During training, we always turn on dropout. But during inference, no one will turn on dropouts. So then there will become some mismatch between the decoding and the training. So when you're doing the decoding time, you turn off the dropouts. However, once you get the data set, you turn on dropout and train on it again. And that dropout makes you improve. And if you do this, the same thing, if we turn off the dropout, you can see, for example, we're doing sampling without dropout, then the first iteration model will never improve anymore. It was stuck at the same point as what the teacher comes from.
You're talking about using dropout on training of the second model on the generated data.
During generation.
During generation?
No. During generation, we never using dropout, right? But during the second training of the second teacher.
Sure. Yeah. So it's just.
So it's not beam search with dropout. It's just.
Yeah. Sorry. So this is written
beam
in a
search
better way.
data.
Beam
train the
data,
model with dropout.
training with
sampling
dropout.
Data, train the model.
Yeah, sampling data with dropout.
Why would you train without dropout?
So we want to analyze where the gain come from. So we want to see why the self-training will improve, because it's not very natural. Even if we're using sampling, we still have gain compared to the teacher itself. So all the data coming from teacher.
You're training now on generated data, which is way easier to fit. So if you turn off dropout on data which is easier to fit, you're just easier overfitting, right?
Yes.
So
Yeah, but
observing an overfitting effect, not a drop. It's something that's specifically true due to dropout. It's specifically due to the data on which you train on. which we have strongly simplified. This is one of the points with the noisy back translation that Facebook had, that when you train on normal back translation, that the data is easier to fit, right? Potentially, so.
But still, I mean, here it's still a different. But in back translation, the noise is coming from in the source, right?
Yeah,
So
you're putting, but you have different sources of noise, right? So
Yeah.
whatever noise you have, it's always going against overfitting. So
you will see there's something we also. I mean, there's other analysis on this.
yeah.
So here, what we want to say is on this control setting, especially for this one, I mean, we actually tuned, so we not just let it overfitting and get a 15 blue score. We always choose the best validation models, and here you have two choices to get this model. One choice is you starting from scratch to train a new model on the teacher's output. And second choice is you starting from the teacher one model, right? So then that is a very control setting. So for example, you can get the teacher one, you train and you generate from teacher one. And once you generate, you're using the same teacher one to continue training on the data you generate. So you will never improve if you turn off the dropout, but it will improve if you turn on the dropout. So that is our analysis here.
But the model will be less general. The model will be less general because it is really overfitting. No? The data is too easy, and then dropout.
So just now what I'm saying is you can do another thing is you continue training from the same teacher model. So the teacher model you generate, and then you using the same model to training on the same data you generate. I mean, you're training on your own output. That is real self-training, right? But in that case, if you turn off the dropout, the model will just stuck at there. It never improves. But if you turn on the dropout, it will still give you improvements. So that is, we think that the dropout this kind of noise is the key which makes self-training actually works. And then the next slide is, because we find that noise will be useful, so why not we just add more noise, which would be similar to the back translation paper was discovered. But here what we do is we inject the syntactic noise in the input words, which is similar to the unsupervised empty noise, like word swap or deletion or the word blank. We further break the source sentence into like X star and then training on Y star. So if you do this, you can see that the pseudo training part, you will never, you just get the same performance. So it actually makes sense, right? Because both source and targets are fake. You will never train something new, real things. However, if you're training on this, you go back to fine-tuning on the real data, you get a much better performance compared to just using the original self-training.
So that's fine-tuning on the real data with the noise injected. So you inject noise and
noise inject only happened in the self-training part. So this after that, the green arrow go back. You training on clean parallels.
Real data is the same. Huh? Real data is the same. Just real.
Then in that case, why do you get the gains in the fine-tuning on the clean data, and you didn't get the gains when you trained on the noisy data?
I mean, so that's because in the noise part. So I mean, things like this. So in the noise part, because our source and target are fake, right? You actually never train something like English to German translate.
The thing is, you got the noise here, and yet this doesn't improve. And you don't have the noise here, and yet this improves.
Yeah, it's because in this process, you finding on this, right? This self-training part, you get a better representation of the model.
It's pre-trained model, but not good for translation.
So the model got pre-trained on the noise in such a way that its effect is invisible until you fine-tune.
Yeah.
It's not useful for the task, right?
Something like you do some self-supervised learning stuff.
Same thing for the efficiency share task. on the same data set, we did noisy forward-backward translation multiple times and trained our student models on that.
Right.
And we got 1.5 per point out of it, right?
Yeah, but he's only getting the improvement when he then fine-tunes on the clean data.
But yeah, because they are doing self-training while we did teacher-student training, right? That's exactly the same thing. So we did the same thing and we got the same improvements.
I see.
Is this published already?
It's submission.
Okay. Because we have this, so our submission to the efficiency share task on the workshop for natural WNGT and EMLP. We did something similar, but not for self-training, but for student training.
I see.
We get the same improvements.
I see. I didn't read that. I should read this. So this one is submitted to unclear 2020, but yeah, I think it's
noisy backward forward translation. So we noisily back translate and then normally forward translate. So create multiple fake data sets and train a student on that. And it also closes the gap between teacher and student quite a bit.
I see. So actually, we also do this. So we also try the wrong translation. So not only inject noise, we do the really, as we said, noisy wrong translate. So you get the X, you translate to Y go back to noisy X. And using the noisy X and the noisy Y, using that one to train the model, and then you fine tuning on the clean data. Then to get even more, I would say slightly better compared to inject the synthetic noise. So I think wrong translate actually, because it's more semantically correct, right? So it may give more improvements, but compared to the synthetic noise, the gain is not too big in our experiments. So we want to understand what actually this noise is doing.
Sorry, can we look at that graph a little more?
Okay.
So is this just the same data you had on the previous slide, or is there something more?
Oh, it's the same. Okay. Yeah, the only difference is this noise part. Either you inject the synthetic unsupervised noise, unsupervised translation noise, or you can do round trip translate.
Okay.
You train a backward model, and you first X get Y prime, and the Y prime go back to X prime.
Is paraphrasing on the target only?
No. Target time is always the fixed.
Paraphrasing on the source?
On source side, yeah.
And how you get the paraphrasing?
How good the paraphrasing?
Now, how do you get the
paraphrasing?
You need to have a backward translation model.
From another
training on the same data set. So training on
phrase-based system or something?
Oh no, just MT. Oh, paraphrasing. It's wrong translate, right? So you translate English to German and then translation back, and you won't get the same sentence, right? So that sentence.
Round trip.
Round trip.
Not
Yeah.
perfect, round trip.
Okay.
Well,
Yeah.
Okay.
What is the largest size of the data that's used there?
So here, everything discussed here is always the same data, the 100K small data
The
set.
language?
English, German.
English, German.
But we did experiments in the later experiment session. So I think we don't have too much time, but here what we show is we want to analyze what actual noise is doing. So we develop a synthetic data set, which is to do the digits summing. We input 4 digits, and it's 11 and 23, and the output is 34. And it's a character level things. So it's very easy to train, but if you're only using 250 pairs, the model will still have struggle to predict something. So the good thing is we can visualize the errors in a 2D map. So we visualize from 0 to 100, 0 to 100, and the arrows like this. And this tool is, first part is a baseline. And when you inject noise doing self-training, then you can see the noise, the output space getting smooth. So we also using our defined matrix to analyze the smoothness when you're applying self-training and applying noisy self-training. You can always see that when you're adding more noise during that, the output space will getting more smooth. And here, the smoothness is only happened for the summing task. It's not generation. But I think it will be generalized to the same thing in translation. So here we have some experiments for more serious experiments. So we have a machine translation task, which on both the simulated way is 100K and a real parallel dataset, which is around 4 million English German with 20 million news crawl. We also did experiments on Flores, which is a Facebook crawl the low resource translation pairs on English Nepali. And we're using the 5 million English sentence from Wikipedia as a monolingual data. And then we do the similar things here. We compare to back translation. So we can see that on English-German, we do see some gains compared to back translation on 100K compared to, I mean, it's not big, but still have some gain by only using the noisy self-training. And on this larger scale case, I mean, it's not large scale, but it's on more data case, you can still get gains even using, so it means that it's not like stuck at some point, but you still have some gain compared to the, so here we don't do back translation because we only have 20 million English part. So we also have experiments on Flores, English, Nepali. So the interesting thing here is that the Flores dataset provides the source from the test set. So the one sentence is translated from English or one sentence is translated from the Nepali. Because there's some source target domain mismatch, so you want to see the effects of self-training. So we do see this. So when we compare to back translation, we can see self-training works better for a sentence from English origin and get worse compared to the Nepali origin, which makes sense because we're using source-side monolingual data to train, right? So it works better on English origin data. And this is what we want to see. And overall, it gets just the same performance on the English. But this blue score is super low. It's because the data set is quite difficult. But still, I mean, using the provided data set, we can get this kind of improvements. So we also do experiments on summarization, which is using the GigaWorld data set. We also do two sets. One is a simulated case, and another one is 4 data case. For the 4 data case, we're using 4 million monolingual data set, which coming from the original GigaWorld dataset. So it turns out the original GigaWorld dataset, they filtered around 4 million documents because they cannot find a good title for that document. But we can use that document as the monolingual data for the self-training. In that case, turns out we can get a very close performance to the very strong pre-training based model at the time. And also, compared to back translation, we can see when we have a low resource case summarization, it gets better performance compared to back translation. Later, it gets worse compared to back translation because when you have more data, then the model is easier to do the summarization. I mean, conceptually, I think this kind of self-training will be much better on summarization compared to machine translation because in summarization, the backward model is more difficult to train, especially for here, I'm using GigaWorld because it's an easier dataset. But if you're doing document translation, document level summarization, your document will be very long. Then it will be very difficult to do a backward model for document summarizations. However, if you do self-training, you can always do this. You can take whatever document sentence and do the self-training like this. We also have some analysis. For example, when we increasing for example, we're using fixed the amount of monolingual data set, and we increasing the parallel data set. We do see the more parallel data set happens, we get more performance improvements on the noise self-training. We also we just fix the parallel data set, but increasing the monolingual data set. Then we can get a more and more better performance. But at some point, for example, we find that after 4 million going to 20 million, I didn't see any improvements anymore. So in this case, there must be some limits because coming from the parallel data set size. And we also tested on the different noise level. So we find, I mean, it's very natural actually. So if we infinitely increasing the noise level, you will never get anything trained, right? So then the performance will get worse. So we find that our first try is like using 0.22 is the best choice we doing all the experiments. And if you're increasing the noise level, you just get worse performance. So there's the last thing is, let's go one step back. So what if we don't using new data? What if we just inject noise on the parallel data set? So what will happen? In that case, we find something very strange. So if we do the same thing like self-training, but the data is coming from using the parallel data set to decode, and using that to train, and then using the parallel data set to fine-tune, we still get performance improvements like 16 compared to original like 15.6. However, if we inject noise in the source, but target is real sentence, then you get a much, much worse performance. Like gets like around 6 if you don't do any fine-tune. And you do fine-tune, you can get 11.
Before decoding?
So if you replace this y star with the real y here, but x is injected noise, you get much worse performance. You need to have noise x and noise y. Then you fine-tune on real, you can get it better. So that is the one.
You need noisy x and generated but not noisy y.
Yeah, generated y. Yeah, not noisy y. Yes, that's true. So noisy y means sampling. That is also bad. So not sampling, beam searched y, but noisy x with arbitrary noise is fine. So
you haven't tried the for translate noise x to generate new y to start something.
oh yeah, I never tried using the noise x to generate y and train something again. I think it should be bad, right? Because the noise x, you just swap words, blank words. How do you expect something will output?
It does work very nicely.
It works?
Yeah.
Yeah, I think it should be a very interesting thing to explore.
So our theory just is that you explore more space, because you know that it's not self-training, it's again teacher-student training. But you now let the teacher translate weird, noisy stuff, but faithfully. So you're just probing the teacher space a little bit better.
I see.
That's what we were thinking. If it's true, it's a different question.
But it depends on the size of the data and the ratio.
Yeah, I think, yes. Yeah, I think this topic is quite interesting. So, yes, for the last slide is what can be the future works. One thing is we never try to combine these things. So we never try to put self-training in the non-autoregressive translation stuff. For example, we both have, as you said, the teacher-student case, but we have more data to train the student. Then I think we can find the same thing you find. Also, how can we get rid of the distillation? That will be a different thing. So, because I always think distillation is kind of hack, which is not so clean. Maybe because it's all because we want to reduce the modality of the data set. What if my model can seek the modes in the training? So you don't need to. You need to have a teacher model to help you to reduce data. So in this case, you can use like a GAN-style training for this kind of models. Also, another thing is, previously I mentioned the noise level actually affects the self-training a lot. So if you have a bigger noise, it's also bad. Then how can we, smartly to identify what noise to inject? So maybe you can have other ways, for example, like a meta-learning or kind of methods to find the best noise level for each kind of self-training or any other pre-training tasks.
Any thoughts about the lottery ticket hypothesis in this context? Because if you want to get rid of, let's say we go back to teacher-student and we have large teacher, small student, and we now look at the lottery ticket idea. So doesn't that kind of contradict the idea that you could actually get rid of teacher-student training? Because you would kind of assume that the big model has a much higher chance of finding a ticket. The small model really doesn't. So now with teacher-student training, you're just moving the responsibility to finding the ticket towards the teacher, and then, okay, I have found the ticket. Now let me show the ticket. Let me show the ticket to you, right?
Yeah, I think Yuan Dong also has some paper in this way. Yuan Dong Tian. He also did something like a teacher-student thing. But in his case, he's trying to find what is the ticket. So what you can. I cannot explain in detail, but yes. I agree. But what I'm thinking is sometimes why we want to get rid of distillation is more because sometimes we don't care our model to capture all the different modes in the data, right? So if we always trying to do maximum likelihood, you're trying to find a model which you're trying to find all the possible things. So if the model only need to care the closest mode for my current generation, then it's done. So yeah, I don't know. But I agree the analysis on the lottery ticket theory.
So I think one of the advantages of distillation is that you're getting, second and third opportunity at doing regularization. And while you might be able to find another technique to do that, right now it's an easy way to get that extra chances at regularization. When you're trying to train a really small model from a large teacher, a lot of the benefit seems to come from the fact that once you go to continuous targets, logits, it's actually just very hard to overfit to logits, whereas it's very easy to overfit to the original Boolean targets. So you can pound the hell out of a small student and just sort of keep forcing it to learn without having the overfitting problem that you would have had from the Boolean targets. So that's where, I think the lottery effect could be real as well, but I think a lot of the benefit that we're seeing in the smaller models is just that the logit data is so resistant to overfitting that you really can sort of keep forcing that student to learn without worrying as much about it overfitting. Now, I think both of these things, the second and third opportunity at regularization and this resistance to overfitting, also kind of is compatible with and explains some of the results you're showing where we're injecting noise, another form of regularization, and where multiple rounds of student-teacher training are helping. And fortunately, you don't have the overfitting problem once you get to the logits.
Yeah. But in our case, so in sequence level, we don't really using logits, right? So
yeah.
Just what I wanted to say. So we train our deployment models on large amounts of translated data. So we're training against hard targets, but we also were able to completely switch out of any regularization. So we're really forcing we're actually happy for it to overfit to the generated data.
Right.
And
but that's because the data is massive.
Yeah, that's the thing though, right? So we generate massive amounts of data. So it's a tiny model. We just, overfit as much as you want.
Right.
So that's,
right.
But now we get the added advantage of having a very peaky softmax, right? So we can go from beam search to greedy search.
Yeah. So one way I think that I do a lot of machine learning in healthcare, and imagine you have patients who, given their symptoms, have a 50-50 chance of dying. So that means some of the patients live and are a 0 in the data set, and some of the patients die and are a 1 in the data set. And the teacher model, which is seeing those 0s and 1s, it has a very hard learning problem, because it has to learn not to try to distinguish between the 0s and 1s. In fact, they might have identical features, and yet, just by chance, some of them live and some of them die. What would be better, of course, would be is if you could just give them all 0.5s. And now suddenly the learning problem is easy because the teacher model doesn't even have to worry about trying to distinguish between, the flip of coin that went 0 for some and 1 for the other, right? It's, if God would give you the probability, suddenly it's a much easier learning problem. But the other solution to this is not to have the probabilities, but to have 100,000 patients who are all just like that. Yeah. And now half of them will be 0s and half will be 1s, and it'll turn out the neural net will never learn to distinguish them because it can't. So it's almost as if you had the soft targets, but you made up for the soft targets by having so much more training data in the first place. Yeah. So I agree that you should get very similar results in that setting.
Yeah, actually, I mean, one thing I always not feel not very clear is because in typical for classification we always using soft targets because we believe it's kind of soft probability is kind of dark knowledge making training much easier, right? But here, everything we using in sequence level training is always using a hard targets, which using beam search to approximate this kind of logics. So still, it's if you think about it's a one hot vector over the whole sentence space, so it's still only 1 point, but it still works much better compared to using the real point. Then that is something I'm not very clear, because it cannot be easily explained because we're using 0.5 or 0.6, right? And also, if we try using soft logics to train this model, usually will fail. So
can you expand on this a little bit?
for example, for training the non-autoregressive models, I never tried in self-training case. I never use it before. But for non-autoregressive model, if you replacing the distillation with soft logics,
Non-autoregressive. Okay.
yeah, in that case, it will never improve.
So have you played around with, because the Kim and Rush paper has this table in the end where they also show that they mix the two distillation methods, hard targets and soft logics, and they seem to be getting their best results from
Yeah, it
those
seems
things.
like this, but I mean, in my previously when I'm doing non-aggressive models, everyone will first try soft, but
No, but they
turn on.
combine, right? They
Yeah.
have hard.
Yeah, I think I also tried combine things. Yeah.
And it didn't work for you.
Yeah.
Good to know. So then I don't need to do it.
And also for
There's
non-aggressive.
some like sampling ratio, weird sampling ratio. It's not that
Did they know? Because I thought that they were just
Wait, were the hard targets generated by a teacher or were they
Yes.
the original hard targets?
hard targets generated by the teacher and the softmax distribution on top of it as a combination. And the paper says that that's like the best method.
It's interesting.
I always wanted to try it, but it feels like a lot of work to actually implement it, so I didn't want to go there.
Yeah, maybe things will change for autoregressive models. So
Yeah.
I think it's worth exploring. But another thing is, for not doing non-aggressive models, so here for self-training, we always trying to go back to fine-tuning, right? But if you do non-aggressive model, because the model is weak, if you do fine-tuning, you originally get a better performance. It suddenly drops if you're training on the real data. So I think these two work are kind of still different. So this is for self-training when these two models are the same. And for the non-aggressive models, will be just only using the data coming from the teacher model and only using the hard targets, no soft targets. Okay.
Any question or comments from the audience? Okay, so let's thank this.
Thank you.